Geometry Unit 14, Section 1, Tangent Segment Lengths. Which figure shows a circle intersected by a tangent, and how can you tell? Well, what we learned about a tangent in the previous chapter is that a tangent brushes the edge of a circle, kind of skims the edge of a circle once and only once. It only hits it in one spot. So we see that this line right here can't be a tangent because it hits the circle in two spots. Same thing with this line right here. That can't be a circle. It can't be a tangent. Hits the circle in two spots. Those are called secants. And they can intersect the circle really at any angle if you were to connect it to a radius or something like that. But a tangent here only hits in one spot. And there's also another thing that's happening here, that whenever a tangent meets a radius or a diameter, which we know is just a couple of radii connected, we get a perpendicular relationship, that a tangent is always perpendicular to a radius of a circle. And that's an important property, and that's our tangent property number one, that a line is tangent to a circle at a given point if it is perpendicular to the radius drawn to that point. So a tangent meeting a radius is perpendicular. Now, if a tangent meets a chord or something like that, that's, tangent meeting a chord, that angle is not going to be perpendicular. But if it meets a radius or a diameter, it's always perpendicular. And whenever we see perpendicular, we see, Pythagorean theorem and right triangles and things like that. So important stuff there. So property one is that tangent meeting a radius is perpendicular. Tangent property number two is that tangent segments from the same point to the circle are equal in length or congruent. And let me illustrate this for you. That here I have tangent AP, and I also have tangent BP, and they are both coming from exterior point P. Now, why are they the same length? Well, to prove this, let's do a little quick triangle proof here. I want to prove these two triangles are congruent. Well, they're both they're both connected to two different radii, radius OA and radius OB. And we know that all radius have to be the same length, of course. We see that the reflexive side that they have in between them must, of course, be the same. So that's a couple of sides. And because it's a tangent meeting a radius, like we said in property number one, they have to be perpendicular. And because they're perpendicular, this reflexive side is a hypotenuse, and we have a leg congruence. So we have a hypotenuse-leg congruency relationship happening between these two triangles. And because the two triangles are congruent, CPCTC then tells us that corresponding parts such as AP and PB must also then be congruent. So that kind of proves this concept right here, that tangents from an exterior point to a circle are congruent in length. So what we're really trying to say here is that AP, tangent AP, is congruent to tangent BP. All right, let's get some practice problems involving these two properties here. So first question, if AB equals 5 and BC equals 12, uh, AC equals 13, um, is BC a tangent to circle A? And so the only way this would be the only way this is a tangent, since it's meeting a radius, we know this is a radius because it's called circle A, and so this is the center of the circle, and so this is definitely a radius. And so if this were a tangent, then this must be perpendicular. And how could I prove that's perpendicular? Well, I could prove it's perpendicular by proving this is a right triangle. And if it's a right triangle, then these three lengths fit the Pythagorean theorem. Does 5 squared plus 12 squared equal 13 squared? That's 25 plus 144 equals 169. And 25 plus 144 is 169. So yes, that is perpendicular. So in the explanation, I would write something along the lines of um, BC is tangent to circle A because the three lengths of triangle ABC fit the Pythagorean theorem, which proves that angle B must be a right angle 90 degrees, and if a radii intersects a exterior line at a 90-degree angle, that line must be a tangent, something something long and complex like that. But basically, by proving it's a right triangle, we proved a right angle, so we proved this must be a tangent relationship because a radii can't intersect a secant and be 90 degrees. It would have to be a tangent, and that's what our tangent property 1 is referring to. Number 2 on the next page. BC is tangent to circle A. Sorry, so now they're telling us a tangent. So if this is a radius, then we know we have a perpendicular relationship. We know we have a right triangle. DC, this little exterior segment, so this AC, this is not a tangent. This is a secant, or at least part of a secant, before we continue. This exterior part over here is 9. BC is 15. Find the radius of the circle. Find the length of the radius of the circle is what we really mean here. So I want to know this length, but not only that, AB is a radius, so is AD. Those are both radii lengths, right? From the center to the circle. But what we said is we know that this is a right triangle because of our perpendicular tangent radius property. So that means that this needs to fit the Pythagorean theorem. So the legs are x and 15. So that's x squared plus 15 squared equals. Now my hypotenuse here is a part that's x, a part that's 9. So I'll need to combine that to be an expression x plus 9. And that's my hypotenuse squared. So there's a good amount of algebra in this chapter with things like this. So x squared plus 15 squared, I believe that's 225, equals x plus 9 squared. That's going to be x squared plus 18x plus 81. Now, how was I able to do that math so quick? This is a very, very important thing, and I've shown you this before in class. We've seen this before, most likely in a video in this course and in other courses. This is what we call a binomial squared, and when we do a binomial squared, that is the same thing as x plus 9 times x plus 9, and we could use distribution to get it. You can't just make it x squared plus 81. You don't just square the things inside. You have to multiply it by itself. And so you have to do x times x is x squared, and then x times 9 is 9x. But how come I don't have 9x here? Well, because there's a second x times 9. So there are two 9x's which will combine to be 18x. And then the 9 times 9 is 81. So the shortcut when you do a binomial squared is just remembering that if you square the front, you get this. If you square the back, you get that. The middle comes from times each other times 2. So times each other doubled. Because, like we said here, we have an x times 9 here and a 9 times x. So it's the same thing twice. So times each other doubled is what gets you the middle. That little shortcut's going to save you a good amount of time on a lot of algebra questions. You know, not just this course, but especially next year when you take Algebra 2. So let me just get my calculator out and ready because I'm likely going to need it for some of these operations. Quick time check. All right, 8 minutes. All right, a couple minutes. We'll finish this up. What we want to do at this point now is solve it. The nice thing here is we have x squared on both sides, so I could zap that, get rid of that. We could subtract 81 to the other side, and this is where I'm going to let the calculator do that math for me. Let me just double check my 15 squared is 225. It is. Okay, cool. And then minus 81 to get that is 144. And of course, I'll have to divide the 18 to solve for x to get 8. So 144 equals 18x, divide the 18, and x equals, what did I say? 8. X equals 8. So the radius length is 8. How about AC? Well, AC is this whole thing. So 8 plus 9 is what AC is, and that's going to be 17. All right, let's finish this up. These are the easy ones, and this is coming from these are all tangents, as it describes up here. And a tangent from an exterior point is congruent, so that means that these two are congruent. These two are congruent. They both come from A, and these two lengths are going to be congruent. So if AR is 2, that means AL is 2. If AB, this whole thing, that's pretty sloppy, but you know what I mean. If that whole thing is 6, that means this other piece must be 4, and this must be 4. If AG, this whole thing, is 5, then this must be 3, and this must be 3. And so if I want to find the length of GB, it's this combined, so a total of 7. So it's just a lot of, these are equal, these are equal, these are equal. Find the lengths. That's real quick. That's real simple for you guys. All right, one more question. AC is tangent to circle G, but not circle D. Circle G has a radius of 5, shown here. And circle D has a radius of 3, shown here. And the two circles are 2 apart. Find the length of AC. Okay, a couple of things. I know this is perpendicular, so I see one big right triangle here. I'm likely going to have to do Pythagorean theorem at some point. But we can fill in more lengths here. This is 5, but this is also a radii of circle G, so this piece is 5. They're 2 apart. This radii is 3. Well, this radii is also 3. That means that this entire hypotenuse length is 5, 2, 3, 3. That's 5, 10, 13. And so this whole length then is my third side of this big right triangle in here. And that's going to end up being 12. I just know 5, 12, 13 as a common Pythagorean triplet. But let's say it was x. That'd be 5 squared plus x squared equals 13 squared. 25 plus x squared equals 169. X squared equals 144. The square root of 140. Well, that's pretty sloppy. Sorry about that. Square root both sides, and the square root of 144, x equals 12. So the length of AC equals 12. They didn't say find x, they said find the length of AC. So that's it. I mean, we also saw that 5, 12, 13, I think, earlier in another problem. That first one where we were checking if it was a tangent. So just make sure if they give you a radius length, if you see another radius in that same circle, you know that length as well. And when you know something's tangent to a circle, you know if it's connected to a radius it's perpendicular, you know it's probably going to form a right triangle. And whenever we talk about the lengths of a right triangle, it involves either trigonometry, sine, cosine, or tangent. That could certainly come up here, but likely a lot of the times it's Pythagorean theorem. All right, guys, so this is Unit 14.1, the last chapter of the year for us, and it involves a lot of things about segment lengths in circles and coordinate equations of circles and area of circles. So it's a lot more circle stuff. It's a pretty big chapter, but it's a really important chapter as well. See ya.